In this lesson, we're going to take a look at conservation of energy. Now, the important thing to notice on conservation of energy is always conserved, which means the total amount we start with is always equal to the total amount we end with. However, not all energy is mechanical energy. And I say mechanical energy is the sum of an object's kinetic and potential energy. So kinetic energy is energy it has due to its motion, and potential energy is energy it has due to forces that are acting on it. So like gravitational potential energy, elastic potential energy, if we had magnetic field acting on something, we could have that. Those are mechanical energy. Thermal energy is the energy of an object's particles. So because it's made up of atoms and molecules and those are in constant random motion, it has thermal energy. And once mechanical energy has been converted to thermal energy, it's no longer mechanical energy. And mechanical energy is not conserved always. Sometimes it is. If friction acts, it's not. Friction does work to convert mechanical energy to thermal energy. If you do work, it's not, because you put energy into the system. You could argue that you use thermal energy to transfer some energy, mechanical energy, to a system. Okay, so conservative forces don't change the amount of mechanical energy. Non-conservative forces do. Non-conservative forces depend on the path that they take. Remember, if I had this thing and I released it from the top of this ramp and it's frictionless, it wouldn't matter if it slid down this incline or just straight down. Its change in potential energy is the same, and so it'll gain the same amount of kinetic energy, and so it doesn't matter which path it takes. The work done by gravity is the same. But if there is friction, falling this way means it will end up being slower. It'll have less mechanical energy because friction got to act on it for that whole distance, whereas if it fell this way, friction doesn't act for as much distance. So friction depends on the path that it takes. It's a non-conservative force. So what we want to do is use the law of conservation of energy to solve a problem. And what I have is a block that's compressed 10 centimeters into a spring that has a spring constant of 2,000 newtons per meter. And I want to know, how high does it go? Okay? And so first thing I have to do is establish a zero height. And I'm going to call my zero height here because I get to pick whatever height I want to measure relative to. Let's start at the low point, and then we can figure out how high above that it goes. So we're looking for, where does it end up here? I want to know this height. Well, we're going to start with a frictionless case. If this is a frictionless ramp, then this is a pretty easy problem because mechanical energy is conserved. So we know initially that it has compressed the spring a distance of 0.1 meters. Tells us right there. We know the spring constant is 2,000 newtons per meter, and we also know it is at rest, and we know its height is 0 because we picked it that way, which means initially its energy, its total energy, which is kinetic plus potential, is equal to 0 for kinetic plus 0 for gravitational potential plus 1/2 of 2,000 times 0.1 squared, which is 1,000 times 0.01, which is 10 joules of energy. That means everywhere along this incline it will have 10 joules of energy. At its very highest point, it stopped moving, and so none of that energy is kinetic. Halfway up, some of its energy would be kinetic. But all we're interested in is, okay, at its final position, how high is it? Well, now, all of its energy is gravitational potential. It's no longer in motion, so its velocity is 0. The spring is no longer stretched, so there's no elastic potential energy. So the only thing that we have is potential energy from gravity. And so our 10 has to equal mgh. Well, 10 equals 1 times 9.8 times h. So h equals about 1.1 meters, whatever 10 divided by 9.8 is. That's how high it goes, right? So I didn't have to use force. I didn't have to use vectors. I didn't have to separate this thing out into directions and figure anything out. All I had to do was use energy at the beginning equals energy at the end. Now, if we look at the case where there is friction, this is going to be a little bit different. So let's say that I do have a coefficient of friction equal to 0.3. Well, now all of a sudden I have a non-conservative force doing work, and I do have to pay attention to that. And that non-conservative force is friction. It's not gravity, right? Gravity is still a conservative force, and the normal force doesn't affect anything because it's perpendicular to the motion the whole time, so it does no work. But the frictional force, which is going to oppose that motion, is going to do negative work, right? And so Fk is equal to Fn mu k, which is equal to mg, Fn is cosine 30 times mu k. So if I know my frictional force, then I can actually still use the law of conservation of energy. It's just that I have to account for any work done by non-conservative forces. So my initial energy, which is kinetic energy plus potential energy plus elastic potential energy, is equal to my final energy, which is kinetic energy plus potential energy plus elastic potential energy. But I also have to account for any work that was done. So plus work. Okay? Well, the work that is done by friction. So this hasn't changed. My initial quantities haven't changed. So I still have 10. And my kinetic energy hasn't changed. It's still 0 at the end. My potential energy has. Now it's mgh, but my height will be different because friction does work the whole time. Plus my elastic potential energy, which will be 0 again. And then I have the work done by friction. I'm going to subtract it over minus the work done by friction. Okay, so the work done by friction is equal to the force of friction, which we found is mg cosine 30 mu k, which mu k is 0.3, so mg cosine 30 mu k times the distance through which friction acts, which is some distance d. But that distance that it acts is this distance, right? And so there's a relationship between d and h. We know that sine 30 is equal to the opposite side, h, over the hypotenuse d, which means d is actually equal to h over sine 30. So we can actually put that in right here, and we can say the work done by friction is equal to mg, I'm going to put my coefficient of friction right here, times cosine 30 times h divided by sine 30. And remember, this is actually all multiplied by the cosine of 180 because this distance is opposite that force, which just makes this whole thing negative. So now I'm going to end up with, I'm going to do some substitution here. I've got 10 equals, don't need to take care of my 0, m is 1, g is 9.8, h is h, don't know it. If I did, my problem would be over. And then minus a minus, which is plus m, which is 1, g, which is 9.8, mu k, which is 0.3, times cosine 30 over sine 30 times h. So the only unknown in that whole equation is h. And if we do the algebra, we're going to end up with 10 equals 9.8 h, sorry, plus, which is 14.8 h. So I take 10 divided by 14.8 and I get 0.68. So our height is about 0.68 meters. And if we look at that, we see it's lower than this, and that's because friction did work and reduced the amount of energy that it had.